Everyone, and welcome to another FLAN talk. Today we have David Chiang presenting for the third time now, and he was one of the first talks in our series. And for the ones who don't know him, David is an assistant professor at the University of Notre Dame and working in NLP and formal grammars and machine learning. And today we catch up on the recent developments in showing lower and upper bounds for transformers expressiveness. And I'm really excited for this talk. Thank you so much for presenting today, David. And you can take it from here.
Thank you. Thanks all for coming. I forgot that this is my third time. I think the first time I was presenting, I think the S4 work. So I think it was actually more of a tutorial type thing, but this is a research talk. This is joint work with my co-authors, Peter Cholak and Anand Pillai. They're in the math department at Notre Dame. Anand works on model theory, Peter Cholak works on computability theory, and I roped them into thinking about some far more practical stuff than they normally think about. And this is work that will be presented at ICML later this year. Okay, so Lena, have you given your talk already on
No.
logic? Oh, you haven't. Okay. All right. So I'm going to give kind of a brief introduction for why I think logic is interesting to the question of neural network expressivity. Finite automata are something that I think this audience knows extremely well. So the kinds of questions that people are able to answer about finite automata, they can recognize a to the n, b to the n, but not a to the n, b to the n. You've got nice results like the pumping lemma, the Myhill-Nerode theorem that characterize, that help you, either prove that languages are not regular or exactly characterize which languages are regular. We have lots of equivalent models of computation like regular expressions and things like that show the robustness of this class of languages. So we've got this very excellent collection of machinery and results characterizing the regular languages. It would be great to have this level of theoretical development for something like transformers, which people are, of course, very, very interested in right now for practical reasons. And it would be great if we could understand the class of problems that transformers could solve exactly as well as we understand what finite automata are capable of. So this is kind of the big picture that I think most people in the room are interested in. I made these slides originally for a different audience, but I think it's good to remind people of what they already know and agree with already. This paper was posted on Hacker News, news.ycombinator.com, and it was really interesting to me to see the discussion of this paper on that board, because people were posting things like, do transformers, can they solve NP-hard problems? And one person said, of course they can. And then one person was like, oh, of course they can't. And the level of confusion that exists about what transformers can and can't do was far worse than I had realized. And so I think that this is a very pressing question to better understand and to better let the public know what's the true level of expressivity of transformers. So okay, why does all this matter? So we understand the relationships between all these different formal systems. So if we can relate neural networks that people are interested in for practical reasons to these formal systems that are better understood from a theoretical perspective, then we'll be able to make more confident statements about, well, transformers should be good at this kind of problem, but maybe RNNs will be better for this other kind of problem, and so on and so forth. And I truly believe that if we have stronger theoretical underpinnings, then we'll be able to make a quicker progress in the practical arena as well. People have tried a lot of different variations of the kinds of formal systems that people in this room work on, and the theoretical literature is filled with all kinds of variations of circuits and logics and automata. And I think they're a goldmine for possible variations of neural networks. So if you can establish a connection between neural networks and formal logics, then you've got umpteen different variations of the formal logic that all correspond to different variations of neural networks. And so I think there's a lot of room for crosstalk in both directions between the two fields. The third reason why I think this matters is the one I'm the least sure about, and that is neural networks are famously not very interpretable. Formal systems are designed to be human readable. So I and probably some of you hope that if we're able to establish these connections, we might be able to improve interpretability of neural networks. But then the natural question that arises is, well, if you convert your transformer into a giant circuit, then how many gates will the circuit have, and would you really be able to read such a large circuit? I don't know, but I always tell people that this is one reason we're interested in establishing these connections is maybe we'll be able to improve interpretability. Okay, so people have related neural networks to lots of different kinds of formal systems. So the oldest body of literature is relating feed-forward neural networks to Boolean circuits, and this is a pretty well-established area. And these two models, I think, are a really good fit for each other. Then there's also a really famous series of papers relating RNNs with fine automata, extending up into very recent work, extracting automata from RNNs and so on. Here, I think that the fit's not as good. If I'm not mistaken, in general, if you take an RNN and convert it to a finite automaton, you can get things like exponential blowups in numbers of states and things like that. And so just as an aside, I've often wondered if alternating finite automata would actually be a better fit and avoid the exponential blowups that people see. But that would be like that's a completely different topic, but if you're interested in that, I'd be interested in chatting with you about that. So there have been lots of interesting papers relating Boolean circuits to transformers. And the difference, of course, between transformers and feed-forward neural networks is that you have a variable width. A feed-forward neural network has a fixed width, and a transformer has a variable width. So you can't relate transformers to individual circuits. You have to relate them to families of circuits, one for each possible string length. And then you need some kind of uniformity condition that expresses how the circuits in a family relate to each other. And personally, I find the whole world of uniformity conditions very, very complicated. And so, just as a matter of personal taste, I have not always found circuit complexity and transformers to be the best fit. Although there are lots of connections between circuit complexity and logic, it seems their fields are closely related, kind of joined at the hip. But just I feel like the way that logics for strings work to me seems like a slightly better fit for studying transformers as recognizers of formal languages. Okay, so logics for strings. So the idea here is that we want to write down logical formulas in some kind of logic, and formulas have true or false values. And so the idea is you pop in a string, and then the formula will tell you true or false. And then so you can use a logical formula as a acceptor or rejector of strings. So I think that unlike automata and similar to circuits, the fact that you have conjunction in both circuits and logics means that you can avoid the exponential blowups that you see in a lot of work on finite automata. And unlike circuits and like finite automata, I feel like this formal systems are automata and formal logics are a little bit of a better fit for sequences of variable length than circuits are. So I really like working on logics, and I think it's a very promising direction for talking about neural network expressivity. All right, any questions so far? No? All right. Okay, so here's kind of a cartoon sketch of previous work. I think the slide might already be a little bit out of date. So here's a summary of some of the previous upper bounds on transformer expressivity. Here I'm focusing just on transformer encoders, and I'm realizing now my slides are a little bit out of order because I have a slide later talking about the difference between encoder decoders and encoders. And it's generally true that work on upper bounds tends to put some limitations on transformers in order to achieve an upper bound. And work on lower bounds on transformers tends to stretch the transformers a little bit in order to achieve the lower bounds. I think it's not always true, but it often is. So this slide, and my paper is no exception. So this slide summarizes some previous work on upper bounds. So Michael Hahn's paper put a condition on soft attention transformers that I'm calling here minimum margin. It says that when you accept or reject a string, there has to be you have to accept with probability 0.5 plus epsilon, or you have to reject with 0.5 minus epsilon. He was able to show under that condition that transformers don't recognize parity. The paper by Sophie Howe and Dana, and I'm sorry, Will, were you on the paper too? The hard max attention paper?
No, but Bob Frank was the third author.
Okay. Yeah, I can't remember who the et al. Is. So they were working with hard max attention or arg max attention and showed that transformers only recognize languages in non-uniform AC0. And then Will's paper, and again, I can't remember who the et al. Is, showed that transformers with saturated attention and log precision recognize only languages in non-uniform TC0. And there's a detail here that I'm missing. Yes, it's a 2023 paper now, isn't it? This is their tackled paper. I lose track.
Yes, yes.
Okay, yeah, so that should be 2023, excuse me. And then the fourth column, this is already out of date. So Will and Ashish published a paper, an archive paper in 2022, showing that fixed precision transformers recognize only languages in uniform TC0. But the paper was very recently updated to use log precision and still uniform TC0. Is that right?
This paper is always log precision. And also this is also a tackle paper, just for the record. But yeah.
All right, I'll need to contact you offline to get straight. So the paper I'm referring to here is the one that was posted on archive and was doing fixed precision. It was using finite precision and then was changed to use log precision.
That's the third one, isn't it?
That's the third one. Yeah. So, the titles have all changed a lot, which is probably why this is confusing. But yes, the third.
I'll have to talk offline about this. This is quite important. All right. Okay, I'm going to move on. Maybe it'll become clearer later. Okay, so the work on lower bounds. So Saruk Bhatta Mishra had a paper a few years ago defining a particular kind of counter machine and showing that these are a lower bound on full transformer encoders. I had a paper with Peter Cholak last year showing that transformers, parity is not exactly a lower bound, but showing that transformers in fact do recognize parity, but you do have to extend the transformers just slightly. So you have to add a component to the positional encodings that actually encodes the position itself. And then many of you here are familiar with the work on RASP, which extends transformers quite significantly. But the cool thing is it develops like a whole programming language that can compile into these extended transformers. So these are some of the results on lower bounds on transformers. Okay, so I'd like to focus on two of these papers, and this is why it's so important to me that I have the result and the paper on the right correct. So something seems to be not right here, but Satwig's paper showed that full transformers have as a lower bound the simplified stateless counter machines, and this other paper showed that finite precision transformers have a TC0, the uniform TC0 as an upper bound. Yes? I'm so confused.
So I think the confusing thing is there are two papers with that citation, and one of them is log, and they're both from 2023. So one of them is
I think this should actually be 2022. I think this was a paper that appeared on archive in 2022 last fall.
Yes. But I guess it's been it also is log precision now, but the previous version was fixed precision.
Right. That's right. You've revised it. Yeah, but I'm still responding to the previous version of the paper, which is a little bit awkward. Yeah. Okay, good. All right. So what I'm interested in is if you prove a lower bound on transformers, then you don't know how loose the lower bound is, and if you prove an upper bound on transformers, you don't know how loose the upper bound is. So I'm interested in, well, can we try to bring these results together and try to sandwich the expressivity of transformers a little bit better? And I don't do exactly that in this paper. So what we show in this paper is this. Oh, I forgot there was animation here. So we define a variation on first order logic. It has this very ungainly name called fuck plus mod. And we show that it is a lower bound on full transformer encoders. And moreover, it is a tighter lower bound than simplified stateless counter machines are. And we also show that this same logic is an upper bound on fixed precision transformers, and moreover, it's a tighter upper bound than uniform TC0 is. So it's not so much that we're sandwiching transformers, because I'm using two different kinds of transformers. It's that there's a single logic, and the single logic is sandwiched by two variations of transformers. Does that make sense? So this slide is the slide that summarizes all the results. So I'm going to make sure that this slide makes sense. And the reason why I think this is useful is there's one and the same logic that is a lower bound on full transformers, but it can't be too loose because we know that it can express anything that a fixed precision transformer can. And an actual transformer that you run on an actual computer is a fixed precision transformer. It has very high precision, but it's a fixed precision transformer. So we have some reassurance that this logic Fock plus mod is not so weak that it's unable to do anything. It's not so weak that it's unable to do something that a real transformer can. On the other hand, we show that it's on the other hand, it's an upper bound on fixed precision transformers, and it's not so loose an upper bound that it can't recognize any languages that are like untransformer-like because it has full transformer as an upper bound. Sorry, I don't feel like this is coming out very clearly, but hopefully the picture is clearer than my words are. All right, does this make sense? Yeah, so we have a single line.
So the two gray arrows are the arrows that you're talking about in regard to models of transformers, right?
Right. Okay, I'll move on if there's no more questions. Okay, so here's a cartoon picture of a transformer as originally defined as used for a machine translation system. You have can you see my mouse pointer?
Yes.
You have a stack of self-attention layers that reads in an input sentence, and then there's a cross attention that moves over to a decoder, and then the decoder will generate a target sentence. So the expressivity of encoder decoders as string transducers is a super interesting problem, but it's just not a problem that we're looking at right now. So we're looking at just the encoder side of a transformer, which is in line with a lot of previous work in this area. And we want to treat a transformer as a language acceptor. So if this encoder reads in a string at the bottom, we're going to assume that there's one special token called CLS. This is comes from the BERT paper. And this will get passed through a stack of self-attention layers. And at the top, there'll be an encoding for CLS. And we'll put a sigmoid layer on just that one position to produce a probability of acceptance. If it's bigger than a half, we accept. If it's smaller than a half, we reject. So I apologize that this convention is slightly different from a lot of other papers. A lot of other papers just use the last word of the sentence. Here, I'm assuming that there's a special word, CLS. But otherwise, this is quite similar to what a lot of other work has done.
David, can I ask a question?
Yes.
So in the last slide, you mentioned that basically you have an encoder decoder problem. So it's a sequence to sequence type map. Yeah. However, so the problem here is if we focus just on the encoder, you're looking at the pre-image of that map, right? And treating that as a recognition problem. So ignoring the image of the transduction, as it were, and just looking at the pre-image. Okay.
Right. So I guess this particular theoretical setup is most relevant to if you're using a transformer as a classifier, so like sentiment analysis or something like that, then like what kinds of classification problems would you be able to solve? Or if you treat the input sentence as a prompt in a transformer language model, and you want the answer to be produced like immediately at the next time step. Like you want the transformer just to tell you yes or no in response to this question, as opposed to you thinking out loud or something like that, then this kind of a model is appropriate. Okay. Okay, so what do logics of strings look like? I think a lot of you are familiar with this already, but I think it's good to look at examples. So here are two simple examples of logics that describe strings. So the first sentence is for all p, q sub 0 of p. And so p is a variable that ranges over positions. So I'll always use p and q to range over positions. And q sub 0 is a predicate that tests whether the symbol at position p is a 0. My input alphabet here is 0, 1. Okay, so in English, this sentence says every position has a 0. So this sentence describes the language 0 star. Does that make sense? So for the string 0000000, it would be true, but for these other strings, it would be false. Okay, the sentence on the bottom is similar, but it introduces a new kind of predicate. So these are called modular predicates. So this means that the position P, it means that the position is odd. So the position P is congruent to 1 modulo 2. So mod 1, 2 means congruent to 1 modulo 2. All right, so this says for every position, if the position is odd, then there had better be a 0 at that position. So in English, this sentence defines the language, every odd position has a 0. So it would be true for these first 2 strings, but not the last string, right? We're numbering the position starting from 0. No, starting from 1 from 1. All right, is this clear?
Is mod a set or a second order predicate? So it refers to like sets of positions then? So
No. So P is still just a single position. This is a first order predicate. And it's modding the actual position number. I don't know if I answered your question or not.
yeah, how do we know the evenness of P?
So that's what this predicate is. It's true for values of P that are odd, and it's false for values of P that are false.
Oh, I see. I see.
It's false for values of P that are even.
I see.
All right. Okay, so now we're going to get a little bit fancier. So now we're going to introduce counting quantifiers. So this quantifier, so this there exists X is now a quantifier over counts rather than positions. So we have 2 sorts of variables. There are variables for positions and variables for counts. So this is there exists a count X, and then this quantifier says the number of positions P that satisfy the body of the quantifier is exactly equal to X. All right, so this is there's a count X such that there are exactly X positions such that the position P has a 1 in it, and X has to be equal to 3. So in English, this is there are exactly 3 ones. All right, so these counting quantifiers are kind of weird because they bind one variable, but they involve a second variable that it does not bind. All right, so this formula would be false for the first two strings, but it would be true for this string because it has exactly 3 ones. Does that make sense? So this is definitely
so the existential quantifier with equal to X is basically a binary or predicate that takes a number and a position.
Yes, but it also binds P.
Yeah. Okay.
Oh, sure. So just in standard first order logic, there is some predicate that you would let you simulate this quantifier. Yes.
Yeah.
Yes, but we don't have binary predicates, and that's actually quite important for these results. Okay, more complicated example. So there are counts X and Y such that there are X occurrences of 0, and there are Y occurrences of 1, and X is twice as big as Y. So this says there are twice as many zeros as there are ones. All right, so it'd be false for this first string. It's true for the second string because there are 4 zeros and 2 ones, and it's false for this third string.
So sorry for interrupting, but how what are the types of arithmetic that you have?
Addition, multiplication, subtraction, and division.
Uh-huh.
Yeah, and the counts weirdly range over rational numbers. Not that you would ever use the fractions, but it actually makes things work out easier if we allow counts to be rational. Yep. Any more questions? No? Okay, great. All right, so this logic is called Fock plus mod. The FO stands for first order logic. So you've seen that there are first order quantifiers.
Oh,
The C
David.
stands for, yes.
John posted something in the chat.
Okay, doesn't the mod predicate assume a binary ordering on string positions? That an even position follows an odd one? Sorry, I don't understand this question.
Oh, I meant that you have like string positions 1 to n, right?
Yes.
So you have to assume the natural ordering on natural numbers, which is a binary relation if you like get down to it, which is what the usual like model theoretic perspective on strings will tell you, right? So you really just have like string positions which are isomorphic to the natural numbers. And so you have to you have to assume that there is an underlying binary relation in order to get like a predicate like mod, which could say I'm even, right? To be true or false.
Saying, but the ordering is not accessible in the logical language.
I see.
Like there's no way to express that x is smaller than y in this logic. I'm sorry, that p is smaller than q.
So that's why you distinguish between positions and those x's, the natural numbers.
Yes.
Yeah,
Yes.
okay, now I get it. All right.
Okay, great. Thanks. All right, so the C stands for counting quantifiers, which you've seen. Now comes the weird part. So there are two sorts of variables. So counts, you can add, subtract. I only listed addition here. Maybe the others are definable in terms of addition. I can't remember, but I don't think it matters too much. So you have arithmetic relations, and you have ordering, and you have equality. So all of these things you can do those things with counts. But then with position, in the sort of positions, the only predicate that you have is this modular predicate. You don't have ordering, which is kind of weird, and you don't have equality, which is super weird. Okay, and then so this naming scheme for logics is pretty standard, except I didn't know how to name a logic that has two sorts of variables, so I used this semicolon. And anyway, so it's kind of a cryptic name, but this is the expansion of the acronym. All right, does it make sense?
Yeah, so I guess the fact that the positions don't have order or equality reflects the fact that basically in a transformer you are looking at a bag of words.
That's right, right. And transformers also cannot test for order or equality of positions. All right. Okay, so how does this logic defines a class of languages? How does this language class relate to some more familiar language classes? So in this logical language, we can define the formal language of majority. So that's this formula here. So for all x and for all y, there is, sorry, these are really hard to read. So there are exactly x occurrences of 0, and there are exactly y occurrences of 1, and x is bigger than y. Okay, so this is the majority language. I'm trying to remember if it makes a difference whether these are for alls or there exists. But we can write the majority language in this logic. Majority is not a regular language. It's also not an AC0. It is in TC0. Here's an example of a language that we cannot define. So this is the language 0 star 1 star. And if you were going to write it down, you'd write something like this, which is not part of the logic. So you'd want to be able to write something like for all P, for all Q. If the symbol at position P is a 0 and the symbol at position in Q is a 1, then P has to come before Q. That's what you would write in like a standard first order logic for strings, but we don't have ordering on positions. So this logical sentence is not part of our logical language. Okay, and this is a regular language, of course. It's also an AC0 language, but this is something that we can't do. And the actual proof that this can't be done in our logic is in the paper. And it's interesting to note, as far as I can tell, transformers also are not able to recognize this language, even with infinite precision, because for sufficiently large strings, there are always going to be two positions that are indistinguishable by a transformer. And so they'll never be able to enforce that all the zeros come before all the ones. It's an incredibly large length beyond which this starts to happen, but I'm assuming standard sinusoidal position encodings. All right. Okay, so there's an upper bound result in this paper and a lower bound result in this paper. So the upper bound result is we want to take any fixed precision transformer and convert it into a sentence of this logic. Okay, so mostly this proof is pretty straightforward because the finite precision really simplifies things a lot, because every function on a finite precision number, it's a finite domain, and so you can always enumerate all the possibilities and write a formula that defines any function from a fixed precision number to a fixed precision number. The only interesting part, there's two interesting parts. Okay, so the proof goes by induction on the structure of the transformer, and so for every single activation, for every single bit of every single activation of the transformer, we need to write down a formula that's true if and only if that bit is on, given an input string. So there's two interesting parts of this construction. One is the position encodings. So if we have sinusoidal position encodings, that's why we added modular predicates to the language, because in order to simulate the sine and cosine waves in the positional encodings, we use these modular predicates. All right, and then the other interesting part, of course, is attention, and attention has to combine an arbitrary number of these fixed precision numbers, and so you can't just wave your hands and say that we can enumerate all the possible inputs and outputs of this function, because this is the only function in the network that doesn't have a finite number of inputs and outputs. So this is where the counting quantifiers come in. Sorry for the typo, quantifiers. So the basic idea here, and if you're interested in the details, you can look in the paper. You can take self-attention, and it boils down to a quotient between two summations over positions. And then a summation over positions can really boil down to a summation over bits. So this picture very crudely shows you a whole bunch of binary numbers are the rows of this matrix, and the row indices are the positions of the string. And if we want to sum up the bits across all the positions of the string, then we use a counting quantifier to do this. All right, so the counting quantifier's job is to perform the summations that are necessary to compute self-attention. All right, and there are a lot more details than there are in the appendix of this paper. So in order to make this happen, you have to move beyond finite precision you have to temporarily move to a higher precision than the fixed precision, and then do the counting quantifiers in that precision, and then you round off back to a fixed precision number. Okay, any questions about that half of the paper? Nope. Okay. So the lower bound, I think, is a little bit more interesting. And our job here is to take any sentence of this logic and convert it into a transformer. And now we're allowing ourselves to have infinite precision in this direction of the proof. And the challenge is that a logical formula can have a really complicated structure. So what would be nice is if we can convert the input formula into some simpler form that would let us define this translation in a more well-behaved way. And this is where I think the fact that we're working in a logic really pays off, because we have some very well-established results for various kinds of logics. So in particular, monadic first-order logic, which I had never heard of before doing this work. Monadic second-order logic, of course, is very well known. Monadic first-order logic is first-order logic where you only have monadic predicates. And there's a nice result that says that with or without equality, there's a normal form for monadic first-order logic. You can convert it into a form where you only use one variable. You can quantify over that variable many times, but you only have one variable. And that's true with or without equality, but in our logic, we don't have equality. Presburger arithmetic, which is first order logic where you have addition, subtraction, multiplication, and I can't remember if you have division in Presburger arithmetic, has a quantifier elimination. So you can take any sentence of Presburger arithmetic and you can convert it into a new sentence that has no quantifiers at all in it. And there are quantifier eliminations results for other logics as well. So these kinds of normal forms are really convenient because they can take a very complicated formula and put it into a significantly simpler form. In particular, the quantifiers are really what make things complicated, and they let you make the quantifiers a lot more well behaved than they are in the full logic. So we can do something similar with our logic here. We can take these two particular normal form results and we can kind of smash them together and get a normal form for our logic. And this is super useful for doing the conversion into transformers. I showed you already in the other direction that we use quantifiers to simulate attention. And so we don't want things like nested quantifiers or one quantifier that contains two other quantifiers or things like that, because we know that we can't do these kinds of things with attention. You don't have attention over attentions or an attention that contains two other attentions or weird things like that. We don't have any quantification at all over so the counts kind of correspond to the activations of the neural network, and we can't do quantification over activations in a transformer. And so the quantifiers are very pesky. We'd like to get rid of them and make them line up in a nice vertical stack so that we can convert it into a transformer. And it turns out that we can do this in this logic. So there's a theorem in this paper that says any formula, any sentence of this logic can be converted into an equivalent sentence that has the form shown here on the slide. So you have a bunch of quantifications over counts. They're all existential quantifiers, and they're all in the prefix of the sentence. And then in the body of those quantifiers, you have this conjunction of these subformulas, and each of these subformulas is a counting quantifier. And then in the body of these, there are no quantifiers at all. Okay, so similar to the normal form for monadic first order logic, there's only one position variable that's used in this normal form. You just need P, you don't need Q, you don't need P1 or P2 or anything like that. There's just P. And that's good because in a transformer also, you have these self-attention mechanisms and you never can attend to two positions at once or anything like that. In this last bit here, Kai, there are no position variables that occur in here. Okay, so there can be count variables strewn anywhere in here, but where the position variables appear and how many of them there are is severely restricted. And there are no quantifications over counts anywhere inside here. So all the quantifications over counts are all at the outside here. All right, so I'm not going to tell you about how to do this conversion at all. Just take it on faith that we can take any sentence of this logic and convert it into this normal form. Yeah, but this is a super convenient form that will let us do the conversion to transformers. Okay, I think the next slide just talks about this conversion at a very high level. So we're going to build this transformer. This is a cartoon picture of a transformer. And the various parts of the formula just become various parts of the transformer. So the psi's, so these psi's compute various properties of the string. They don't have to do any quantifications. So those psi's are computed by the embeddings and the first feed forward layer. Compute all of these psi's. And then the counting quantifiers have to count how many positions satisfy all these different properties. Right, so each psi I is some property that's defined in terms of P. Then the counting quantifier's job is to see how many positions satisfy those quantities. So we use a self-attention layer to count up how many positions satisfy each of these properties defined by the psi's. Okay, and then there's this last bit chi that enforces whatever constraints between the counts we're interested in. For example, in like A to the n, B to the n, we'd count up the number of A's, count up the number of B's, and then you check that the count of the A's is equal to the count of the B's. So here, like you'd have a clause here that counts the number of A's, you have a clause here that counts the number of B's, and then you'd have a constraint that says those two counts should be the same. Okay, so that final constraint happens in the second feed forward layer. And then that will let us produce the final answer. And so then the accept reject decision will be the same as the truth value of the formula. All right, so any questions about how this construction works? And again, all the details are in the paper.
So it's a fixed number of layers.
It is a fixed number of layers. Yeah, it's two layers. Yeah, so one of the weird consequences of this is you can take any finite precision transformer, convert it into this logic, and then convert it back to a transformer, and it's guaranteed to have 2 layers. Now, so any finite precision transformer can be converted into an infinite precision transformer that has 2 layers, which is kind of a weird result. But that seems to follow from the 2 directions of this proof. I mean, it would be huge, right? This is the universal approximation theorem is the same way, right? You have 2 layers in this feed-forward neural network, but the width could be enormous. So the number of dimensions D model could be enormous for this network.
David, how do you compute averages over these x sub I to big X? Like, do you since they're rational, since the counts are rational numbers, do you compute them, and do you round them somehow, or do you?
Yes, some rounding has to happen at some point. Oh, in this direction of the proof?
I guess in general.
I always get these 2 directions of this proof confused. So in this direction, the attention's job is to compute a weighted average, right? So in this case, this is related to what Dana raised. Yeah, so in this case, the self-attention is always uniform. Yeah, so it takes a uniform average over these x's at this second self-attention layer. And so that's how this is where the averaging happens.
Okay, cool.
So did that answer your question?
Yes.
And this
so it probably matters to the other direction of the proof more, I guess.
Yeah, in the other direction, we use the counting quantifiers to do a summation, and then you round to the no, the rounding happens later. So you work in this extended precision, and you can do the division in this extended precision, and then you do the rounding afterwards, if I remember correctly. But definitely some rounding has to occur at some point. Yeah, so did that answer your question?
Yes.
Okay,
So
great.
this is arbitrary precision rational?
This is I think is real, actually. I mean, this is a full transformer, so there are exps involved. Oh, the exps are only involved in the attention, and I just said that the attention is always uniform, if I remember correctly. So is everything rational? Maybe everything's rational in this network. I could be wrong.
Also, if I understand correctly, I think everything is log precision as well. Like you can have constrained precision and still have it work out.
I think you're right. Yes. Yeah. So, okay, so now that kind of touches on future work. For future work, I would really love to change the other direction of this proof to take a log precision transformer as input. So this is something Will has done in a couple of his papers, and I think log precision really is the right way to go. But so far, the result is just for finite precision in the other direction. Seems a lot harder to convert a log precision transformer into a logic, but that's what I hope should be possible in the future.
The proof treats the bit positions individually in the formula, so that the formula wouldn't be fixed if there were log positions in that sense, right?
Okay. Yeah, I'll have to think about it more. All right. Okay, so this is open questions. So I mentioned a number of variants of transformers that people have studied, and I just kind of displayed them all over this slide. I think the relationship between these different variants is really an interesting question in and of itself, because I think most of these variants are interesting in their own right. So this question mark here, why did I put this question mark here? I don't remember, I'm sorry. But so one consequence of the results in this paper is that fixed precision is a subclass of uniform attention. And it'd be interesting to work out the relationships between many of these other variants. Are any of these others obvious or no? Uniform is obviously a subclass of saturated. Saturated is obviously no, not obviously a subclass of standard transformers, or it is it? It's not obvious. Yeah, so I think many of these relationships deserve for further study. Oh, yes, okay. So some of these have been worked out and some are still open questions. All right, so what's still missing from this network, this logic? I think I've gotten ahead of myself. I think actually these slides are saying some of the things that we already talked about in the discussion. So this particular network that we converted from the logic only uses uniform attention here. It only has 2 layers. And it's interesting that only this attention head gets used. So all these attention heads don't actually do anything. So they do what they do, and then we throw the result away. And so it seems like this transformer that I'm constructing here seems like significantly like less powerful than a full transformer. So that's interesting and suggests that as a lower bound on transformers, this logic FOC plus mod is not as tight as we want it to be yet. I very much doubt that FOC plus mod is equivalent to full transformers. I'm almost certain of it. And this is kind of the intuition for why this doesn't seem to be using the full power transformers. So what kinds of extensions can we make to the logic? I think these are all questions for future work. So let's see. So for future work, if we wanted to convert, if we wanted to actually find a logic that was exactly equivalent to arbitrary precision transformers, then we'd need to be able to do full multiplication and division, as well as exp, as well as square root in this logic. And this seems really challenging. And in particular, I think multiplication is the really problematic part. And seems to really increase the power of the logic quite a lot. And I think I've had some conversations with Will about this. This is related to like the bit predicate that's sometimes used in these logics, really increases the power of the logic a lot. And I think if we want to go for a proof that's actually a two-way equivalence between a logic and a transformer, we have to do something to limit the power of multiplication. So maybe separating the variables into sorts would help. Maybe some sorts can be multiplied and some sorts can be multiplied, but I think that that is the big challenge, is figuring out how to appropriately limit the power of multiplication. So the normal form that I've shown you definitely relies on particular properties of this logic. So as soon as you do something like add multiplication, then something is going to break. In particular, I cited that Presburger arithmetic has quantifier elimination, and that is only without multiplication. I think I must have misspoken earlier in the talk. As soon as you add multiplication, then you have piano arithmetic, and that definitely does not have quantifier elimination. So something's got to change in the steps of this proof. But it would be really interesting to dig deeper and see how that might be done. Okay, here's my last slide. So hopefully this was an interesting introduction to logic for describing formal languages and how they relate to neural networks. I think that this is a really promising direction to explore further the connections between logic and neural networks, especially transformers. So this logic FOC plus mod is the first result that I'm aware of that's simultaneously an upper bound and a lower bound on two different variants of transformers, and I think this is a valuable approach to take a formalism and sandwich it between two variants of transformers, and maybe as time goes by we can tighten both bounds and maybe at some point arrive at a full equivalence result between some logic and some variant of transformers. And I don't know yet what variant of transformers that will be, possibly log precision transformers. But I think this whole enterprise of studying the expressivity of transformers is as much a search for the right formal model as it is a search for the right variant of transformers, which makes the problem kind of complicated. The fact that both sides of the equation are moving targets, but I think that there's a lot of uncertainty on both sides, and this is a strategy for helping them to converge both sides on the right thing. So we have upper bounds. I think they're tighter than before, but we still don't have an exact characterization of something that's exactly equivalent to transformers. So I think that would be a really good goal to work towards. All right, so that's all I have today. Thanks very much for listening and for your questions. I'll be happy to take any more questions that you have.